Recursion. Let's make it easy. In the next few minutes, the call stack, the base case, and backtracking will finally click. But first, look at this code. A function that calls itself. Most beginners panic. Won't it run forever? Here's the secret nobody tells you. Recursion isn't a function repeating forever. It's a function asking a smaller version of itself for help and waiting. Think of nested boxes. Box 5 can't answer the question alone. So it opens box 4 and asks. Box 4 opens box 3. And so on, until one tiny box finally knows the answer. A recursive function works the exact same way. It solves a big problem by asking itself to solve a smaller one. Every recursive function needs exactly two things. 1. A base case, the moment it stops calling itself. 2. A recursive case where it calls itself with a smaller input. Miss the base case, and it never stops. Here's the simplest example, a countdown. Let's trace countdown of 3. It prints 3, then calls countdown of 2. That prints 2, then calls countdown of 1. Each call doesn't disappear, it gets stacked. This stack of paused function calls is the call stack. Every call is one frame, placed on top. Now n is 0. The base case runs. It prints done and returns. No more calls. The stack stops growing. But here's the part most beginners completely miss. Each pause function was just waiting for the one above it to finish. So now they return, one by one, top to bottom. Countdown of 0 returns. Then countdown of 1 finishes. Then countdown of 2. Then countdown of 3. Recursion goes down by calling and comes back up by returning. Countdown didn't return a value. Factorial does, and that's where recursion gets powerful. 5 factorial is 5 times 4 times 3 times 2 times 1. Watch factorial of 4. 4 waits for 3. 3 waits for 2. 2 waits for 1. 1 hits the base case and returns 1. Now the answers flow back up. 2 times 1 is 2. 3 times 2 is 6. 4 times 6 is 24. Comment stack if the call stack just clicked for you. Here's the trick that removes the fear. Don't trace every call in your head. Just trust that the smaller call returns the right answer. Ask 3 questions. What's the smallest answer? How do I shrink the problem? How do I combine the result? For factorial, smallest is 1. Shrink with n minus 1. Combine with n times the result. That's it, a formula you'll reuse forever. The logic is identical in Java, only the syntax changes. Here's factorial in Python and Java, side by side. Same base case, same recursive call. Once you get the idea, you can write recursion in any language. Now the 2 mistakes that trip up everyone. First, no base case. This countdown never stops. The stack keeps growing until the computer runs out of memory. That's a stack overflow. Second mistake, a base case that you never actually reach. This one moves the wrong direction, n plus 1, so it runs away from 0 forever. The rule, every recursive step must move toward the base case. Now the scary sounding one, backtracking, is just recursion with 4 steps. Make a choice, explore it, undo it, try the next one. Picture a maze. You pick a path, hit a dead end, walk back, try another. Backtracking isn't a new monster, it's recursion with an undo button. Let's generate every subset of 1, 2, 3. For each number, you have 2 choices. Include it or skip it. Start with an empty path. Choose 1. Choose 2. Choose 3. That's a full subset. Now we undo. Pop 3. From here, skip 3. That's another subset. Pop 2, and this time skip 2, then choose 3 to get 1, 3. Pop again. Watch the pattern. Every append is a choice. Every pop undoes it. And each time we reach the end, we record a subset. Append is choose. Pop is undo. Recurse is explore. You'll see this exact pattern everywhere. Subsets, permutations, combination sum, n-queens, Sudoku, maze solving. Whenever a problem says, try all the choices, recursion and backtracking are usually the cleanest tool. So when should you use recursion? Loops are perfect for simple repetition, counting, walking an array. Recursion shines when a problem naturally breaks into smaller copies of itself. Trees, divide and conquer, backtracking. Recursion isn't just a loop. It repeats work using function calls in the call stack. A quick but important note on Big O. For linear recursion, like factorial or countdown, the time is O of n and the space is O of n. But backtracking is different. For subsets, we try every include or skip choice, so the time and the output both blow up to O of 2 to the n. The call stack depth, though, is still just O of n. So linear recursion is cheap, but exploring all choices explodes. Lock it in. Recursion is 3 questions. What's the base case? How do we shrink the problem? And what happens when the answer comes back? The call stack stores every active call. It grows going down and shrinks returning up. And backtracking is just choose, explore, undo, try next. If recursion ever confused you, save this and rewatch the call stack section once. That one idea unlocks almost everything. Next, we'll use recursion for tree traversal and real interview problems. Subscribe to Code Clarity DSA and comment stack if the call stack finally made sense.